All right, good morning all. Sorry about those technical glitches, and thanks to Eleni for helping me out with her computer when mine failed. And as you know, I'm greedy with your time, but I thought it is worthwhile spending another 2 hours on computer vision problems because, or on convolutional architectures, because wherever we look at phenomena that have complex spatial organization in environmental physics, in medical physics, in astrophysics, we typically have spatially resolved sensors, also known as cameras. And for this type of imagery, there are only two types of architectures used today. On the one hand, the convolutional ones, which we started talking about last time, and then modern vision transformers, which, however, also the modern ones also use convolutional elements. And we will see many ideas that are that permeate modern machine learning. So tricks on how to train systems with many parameters if you don't have access to a lot of labeled training data. So tricks for unsupervised or semi-supervised representation learning. And these ideas are more generally applicable beyond any single specific application. All right. The other reason why it's worth talking about them is because these type of architectures, they were really the first place where deep neural networks really succeeded, where they really managed to do a lot better than anything that was previously seen. And this was partly spurred on by the advent of new benchmarks. So this is a benchmark colloquial known as ImageNet, and we here see results from the 2012 paper by Hinton and Krzyzewski, the paper on AlexNet. And you here see the variety of images that were used in this benchmark. And if we looked at previous work, so let's say early 2000s, you could write one PhD thesis about detection of ships in images. Yeah? And already detecting ships in images, it's maybe not, if you forget anything about, everything you know about neural networks, if you think how would you detect a ship, it's harder than it sounds actually. Because, if you just look at sailing yachts, perfect sideways picture, it's kind of easy. But once you have sailing yachts all the way to container ships, and if you take not just one point of view, but here like an aerial point of view, it's always a ship to a human. But if you look at it pixel by pixel, this compared to a small sailing yacht or rowing boat seen sideways, pixel by pixel, this is dramatically different. So, as I said, you could easily write one PhD thesis about the detection of ships, and you could write another one about detection of motorcycles. You could write another one about detection of dogs. But this benchmark had 1,000 different classes. So that's a lot of PhD theses. And before neural networks became successful, what the community then did was to look at visual bag of words approaches. So one would try and take image patches, and then if we take let's say if we take a tiny image patch, so if we take just 8 by 8 pixels, that's a 64-dimensional descriptor. So in the 64-dimensional space, one could cluster, and then one could ask in a particular image, how often is a particular cluster being observed? And you would do that for thousands of clusters, or hundreds at least. And in that way, you could represent an image in terms of this histogram of how often has which cluster been activated. And now you had a constant dimensional description of your image, even if the image became larger or smaller in pixel dimensions. And this could be fed into shallow classifiers like decision trees, support vector machines, and so on. So this was the state of the art, broadly speaking, before the advent of neural networks. And then came AlexNet, trained on 2 GPUs of 3 GB each, because that was the most that was available at the time. So for comparison, the machine which we are currently procuring, a single GPU has 150 GB and it has 8 of them. So, life has become a lot easier for us, or we can, work on harder problems. But even what they accomplished was already quite impressive. So we see here the true class, and then we see the softmax or soft argmax activations of the next most probable classes. So here the neural network thinks it's probably a container ship, but it could be a lifeboat, or maybe an amphibian, or maybe a fireboat, or a drilling platform. I mean, drilling platform is not so far off here. And then, of course, these examples were cherry-picked. So here, for example, the true class of this image was grill. That's this part of the car. And the neural network predict it's a convertible. So what the authors wanted to say here, look, that's a very forgivable error. Or this one here, the neural network saw a Dalmatian, or maybe a grape, or maybe an elderberry, but the true class here was cherry. So cherry-picked example. So this was a radical break with what had been possible before, and it ushered in this new era of deep learning. Now, the kind of architecture that was popular in those days was of this type here. And this is not AlexNet, but this is VGG16, which you will also look at in the exercises. And I'm showing it here because it has a few typical elements. So we put in a large image, and we want to come out here with a one hot vector. So this vector has 1,000 entries. And for this particular problem, where we try to predict 1 out of 1,000 classes, we put in any image, and then we look at which elements of this vector are largest. And all elements are between 0 and 1, and they sum to 1. So how do we go from an image, which is maybe 224 by 224 pixels, to something which has no spatial resolution at all? And we saw 2 mechanisms last time. We saw transpose convolution, and we saw max pooling. The latter is what's being used here. So the input is, so any image is rescaled to 224 in the x dimension, 224 in the y dimension, rescaled or cropped, whatever. It's made to have these sizes times 3. 3 is for the red, green, and blue channels of the image. And then came these convolutional layers. So here we have a convolution stencil, which is 3 by 3 by 3. It's 3 by 3 spatially, and it's 3 because we have 3 layers or channels here, 3 channels. And a total of 64 of these filters are being learned here. And then another 64 filters depending on those are learned. And then comes the first max pooling layer, which reduces the spatial extent by half along each dimension. More convolution layers, another max pooling, and so on and so on. And at this stage, all spatial information has been lost, or it's somehow encoded in this vector. So here we have something which has, it's an image, if you wish, which has a single pixel, but it has 4,096 channels. So we have mapped any input image of this size to a vector with 4,096 entries. So our entire image has become a point in 4,096 dimensional space. And now we know what to, if we want to classify points in some Euclidean space, we know what to do. We use a multi-layer perceptron, and here multi is a bit exaggerated, like it has 1, 2 layers and a softmax, and that's it. And so the paper was quite influential because this architecture could be trained robustly, it performed well. In these early days of convolutional networks, there was also a lot of debate about how big should the spatial filters be. And they found that 3x3 worked well for them. It was better to have more layers as opposed to bigger filters. And this view held for many years. And it is being challenged more recently. So if you have the training data and if you have the GPUs, then modern architectures like the ConvNext that I briefly mentioned last time, that are on par with vision transformers and computer vision tasks, there the filters are again becoming a little bit larger. All right, any questions so far? Good. Then, Peter, I would like to ask you to stop the recording, please. And remote sensing, this type of remote sensing problem, it has many applications, of course. One that I've seen quite a lot in the literature is on the prevention of forest fires. So you can look at which areas are particularly dry, and you can, take preemptive action or, station observers on the ground and so on. It is used a lot in agriculture these days to see, in the huge Midwest, which field is, where the crop is going to mature when, to try and plan and schedule where the harvesting machines should go. And of course, plenty of military use. But this type of imagery where we have spectral images as input is also very prevalent in astronomy. And I was saying that it relates to this type of architecture here because, well, we here see 3 channels. This was 224 by 224 spatial times 3 channels for RGB. Instead of 3 channels, we can now have 15 if it's Sentinel, or we can have, however much your sensor gives. Yeah? So you will have a spectral image as an input. And to the architecture, if we want to, classify, for example, the risk of this burning 2 months down the road, to the neural network architecture, this changes almost nothing. What it does change is the size of the first filters. The first filters would no longer be 3 by 3 by 3, but they would be, for example, 3 by 3 by 15 if we have 15 input channels, but the remainder of the network could be unchanged. Except, if we have 2 classes here, then we will want a vector with 2 entries here and not 1,000. So, and now if you compare this to what a shallow classifier would give you, shallow classifier like a decision tree or a support vector machine, they will look at each spectrum individually. But in real phenomena, so for example, if you want to classify, is this a city or not? As you know, city is not homogeneous. We have roads, we have roofs, and so on. And what convolutional networks can do is take into account this spatial context of patterns it observes to come to a reliable or more reliable decision. Yeah, so if the neural network wants to learn that spatial context is not useful, then it can always decide to not use it. So in the extreme case, in this 3 by 3 by 15 filter that I mentioned, it could decide to use, just a central pixel, for example. But it can also decide to use that spatial context. And what it learns in these first layers is shown here. So when you train a convolutional neural network, the first layers very often look like this. And these happen to be the kind of processing that we also see in our primary visual cortex. So basically what we see here are edge detectors and blob detectors. Yeah? So this is like a finite difference operator in this direction. So it detects edges that are oriented like so. Or this one here detects more blurry edges which are oriented horizontally. This one detects not edges, but this is like a second derivative operator. You see you have a sign minus, plus, minus. This is a second derivative operator in the horizontal direction. So we have these filters at the various orientations and at various spatial frequencies. So both for low resolution patterns and for high resolution patterns. And usually this is what the filters in the first layers look like. And this again is from the AlexNet paper in particular here. Okay. By the way, I will show a few pictures and make many words, but I will not write anything on the blackboard. So if you want to take notes, please do. Okay. This was image classification. So input is an image and output is a class label for the entire image. Another problem that we frequently see is semantic segmentation. So segmentation means we partition an image into regions, and semantic means we partition according to different classes that different regions may have. So one way of putting it is we insert an image and we output a class label for every pixel. And this is used a lot in, for example, medical physics. I'm showing a few pictures here. These are different problems from medical physics where we have, for example, either computer tomography or MR images, and the task can be to segment out organs, to find the liver versus the spleen, or to find, maybe label pixel-wise, do we have a lung tumor or not, or label pixel-wise, do we have a brain tumor or not. So we here want an information for each single pixel. And a typical architectural motif is the unit or the hourglass network. It's basically the same idea, just invented in parallel by different groups. This one here was invented in Freiburg by Olaf Ronneberger. And let's look at what it does. So it starts with a high resolution version of the image. You here see the spatial extent and the number of channels. Yeah, so if it's a single channel, this means we just put in a gray value image here, and then come convolutional layers. In this case, 64 different filters are being learned. And if you look closely, a few pixels are being lost here. Yeah? 2 pixels are being lost, and another 2 pixels are being lost along each dimension. And this is because in the original paper, the authors made this decision to use convolution with the valid option. So if we have an image and if we have a convolution filter, what happens at the very border of the image? We either need to pad the image with zeros, or we can reflect the image at the border. But basically, we need to make some arbitrary choice to produce a result of the convolution at the very border of the image. Or we can say that we only use the output where we don't make any such arbitrary choices. And this is what has been done right here. And this is why we start with 572 by 572, but end with something a lot smaller here. in more modern implementations, people tend to just ignore this problem, yeah, and keep the spatial resolution constant here. All right, now from here to here, we have this, in this case, a max pool or a transpose convolution can be used. So here we have half the spatial resolution, but the number of channels increases substantially. Again, the spatial resolution is halved, but the number of channels is further increased. And here we have a really low resolution version of the image. So here we have a 32 by 32 summary of the image, but with 1,024 channels. And so down here, this is also called the semantic pathway. So here we have low spatial resolution, but very rich description. And this helps deciding, what is happening in that region. Is this a spleen or is it a liver? But then for segmentation, we want to precisely delineate the border of the region. And for this, we need the high resolution. And this is called the geometric pathway. And indicated by this arrow here is a skip link. Now, in the original formulation of the architecture, what happens is that this is a standard convolutional layer. This is an upsampling, and the two have been concatenated. This is why there's this wide blue pattern here. But rather than concatenate, in more modern implementations, the tendency is to just sum these two up. Okay? And you do this iteratively, and you end with something that has the same spatial resolution as the original image and as many channels as you want to discriminate, as many channels as classes that you want to discriminate. Okay, and in this type of architecture, first published in 2015, it's still state-of-the-art in medical physics applications, and basically for semantic segmentation nowadays, you either use something along the line of vision transformers or you use that type of architecture, in particular when you don't have enough data to train a transformer from scratch. All right, here are hints from a former PhD student, Alberto Bailoni, who now works at EMBL, on how he would configure such a thing. These hints are from 2020, when we still used that type of architecture, and I cannot, tell you the 2022 version or 2024 version of this now. Okay, and by the way, so for people who were not here in the first hour, all the images that I'm showing, you do find them here, yeah? All right. This is not a physics application, but one physicist Daniel Kawecki worked on for his master's thesis in my lab at the time. This was from a problem called Cityscape, another benchmark. And well, here you could put in natural images and get out a pixel-wise distinction for, is it a passenger, is it a road, is it a traffic sign? And these are, of course, super important for industrial applications, for automated braking systems and such, where you let the car decide if it wants to make an emergency braking. I'm not showing the video now. I put it in there mainly for the cool music, and also because this was quite impressive at the time, because so it tracks these people dancing, and the thing is that explicit tracking is not at all needed. Instead, it really processes image by image separately, and it does it so well that even when there's very heavy occlusion, as you see here, between these humans, it works astoundingly reliably. Now, the pictures from these many benchmarks here, they come from a paper that has been very popular in medical applications. It is called NN-UNet, where the NN stands for no new unit. It is from the lab of Klaus Meyer-Hein here at DKFZ. And Fabian Isensee, the first author, he actually studied molecular biotechnology and wrote his master's thesis in my lab, and then went to Klaus for the PhD and did this very, very successful piece of work. And what a no new unit does is that it does a lot of hard-coded pre-processing, and that has been sufficient to earn the #1 spot on around 30 different benchmarks from the biomedical domain. And these hardwired decisions, they look, for example, at what's the image modality. Is it a CT or an MR or a microscopy image? And this, together with the histogram of intensities, is used to make an informed decision about what kind of normalization do we want to use. Do we want to use the logarithm or the square root or you know, whatever of the pixels, and how do we want to subtract the mean? Then it makes some hard-coded choices about how to resample the spatial dimensions, and you know, all kinds of things about what's a useful patch size, what's a useful batch size, and so on and so on. You see, these are the many hyperparameter or the many user design choices that you have to make when you train a neural network. So very powerful architecture, set of architectures, but very many choices to make. And it makes all of these choices based on rules. There are some things it doesn't change, like it always uses the same optimizer, always uses the same learning rate, and so on. And okay, I'm not going through the details here, but this has been empirically a super successful work to solve real problems in the real world. All right, this was semantic segmentation, where we classify each single pixel. But sometimes we want to find, we don't want to classify pixels, but we want to group pixels. And problem that was the focus of my lab's attention for a decade was the connectomics problem. So here we were looking at super high resolution images of the brain. So here these are serial sectioning, electron microscopy images of, I forget what kind of brain. And the task was to try and see where all the neurons go. And you know, what do we see here? Well, there is some heavy metal staining used, and that stains in particular the membranes, but we also see these dark blobs here. These are mitochondria. These are the power stations of the cells. And then we have occasionally here this would be a synapse that also stains. But now for this problem of grouping, one can use some training data. Yeah? So people sitting down and patiently labeling membranes. And we didn't do this ourselves, but luckily other groups did supply some training data. And then we would use a convolutional neural network to produce this kind of boundary map. And given this kind of boundary map, one way forward is to then group pixels, and the result here would be this clusters of pixels which we are very highly confident belong together. But then the question is, which of these clusters should be further merged? And now that's not the only way to do it, but the way we did it is to formulate this as a graph partitioning problem. So to decide for each of these boundaries, do we want to keep it or not? And these are decisions which you cannot do independently for each boundary. Because if, for example, I decide that this boundary I want to keep, and this boundary I want to remove, and this boundary I want to remove, I have a contradiction. Yeah? On the one hand, I have information that these should be separate, and on the other hand, I have information that they should be connected. And if you want to not admit this kind of contradiction, you have to solve an NP-hard graph partitioning problem, which on small instances you can solve to perfection, and on larger instances you need some kind of heuristic. Yeah, and of course, what's shown here is just a tiny part of the whole data. So we did resort to heuristics because the original data is, billions and billions of pixels, and that translates to still millions and millions of these coarse-grained superpixels. And hence, for realistically available hardware, memory, and so on, you will need some kind of heuristic to solve the problem. Okay, and then this makes for pretty pictures. So shown here, that was the work of Björn Andres, who is now a professor in Dresden, that shows you a tiny subset of the neurons in this chunk of data here. The data itself, by the way, was acquired in Heidelberg. This is from the Max Planck Institute for Medical Research, where Winfried Denk used to work before moving to Munich, and he was the first to be able to acquire this kind of high-resolution imagery with a consistent quality. And these efforts have since been scaled up. So a lab in Janilia Research Campus did this for an entire brain of a fruit fly, and the crowning achievement of this line of work has recently been the Janilia Research Campus and colleagues. They recently developed this suite of 9 articles in a single issue of Nature that describes the kind of circuits they find and the interpretation of this type of data. More pretty pictures. These are images from a collaboration in plant biology. This was led by Alexis Maisel, who is a professor here in the Center for Organismal Studies, just across from Mathematikon. And you see here microscopy images from different parts of different plants. So this is part of a root. This is, other. So these are different parts from different plants, but to analyze how they develop their shape during development, it is useful if you are able to segment these. And that was the work mainly by Adrian Wolny and Lorenzo Cerrone, a PhD student in Anna Kreshuk and my lab, who worked on basically a version of this pipeline here to produce these high quality segmentation results on plant 3D cells or 3D images of plants. All right, any questions so far? Okay, then let's have a break until 10 o'clock. And after the break, I want to talk about more useful architectural motifs and about more recent ideas on how to pre-train such systems when you don't have training data. And announcements. I have 2. If you want to discuss anything, but in particular, things about your studies, or where would you, what group in Heidelberg could be interesting for you, given your own interests, or what do you want to do later in life and so on. If you want to discuss whatever, you can come this Thursday at 4:15. And next week we will have a very special edition of this lecture, because on Thursday this week we will talk about graph neural networks. So we will go to making predictions about sets of objects, and graph neural networks with their permutation equivariance are a meaningful architecture to do that. And that will be the basis for discussing also the attention mechanism, and that in turn is the basis to talk about transformers, the technology behind large language models. And on Tuesday next week, we will have a special guest, Letizia, who is now working for the LLM company here. What are they called? Aleph something? Aleph Alpha? And she has a very popular YouTube channel. Is it okay if I open a tab on this? Let's see. Okay, I'm just typing it here. You can look for it yourself. This is Miss Coffee Bean on YouTube. She has this popular channel about how large language models and such work, and she will come here, and so training large language models is her day-to-day business. So I think she will be able to give a great first-hand account of how they work. And Letizia did her bachelor thesis in my lab many, many years back. And I'm, of course, very happy to see the things that she has been doing since. So that will be Tuesday next week. Tell your friends. This should be interesting. And it's going to be a technical lecture. Yeah. So what you need, it builds on what we have discussed until then, in particular also on Thursday of this week when we talk about the attention mechanism. So it will be a technical lecture, but whoever knows what the attention mechanism is invited to then join for Tuesday next week to hear more about this. Very good. Let's have a break until 10.